Assalamu alaikum. This presentation is a compilation of all my lectures on the core concepts in statistics for medics, so as to introduce a medic to the 12 core concepts in statistics within 1 hour. We'll go through these 12 core concepts in statistics: the types of the data, how and why check for the normality of a data distribution in a sample, the parametric and the non-parametric tests needed, the probabilities relative to the area under the normal distribution curve and the z-score, the p-value, probabilities related to the multiples of standard deviation, the p-value and its limitations, and how to correct the p-value in multiple testing, and then the confidence intervals and the population mean, the type 1 and type 2 errors, and what does it actually mean a 90% power of a study, and the effect size versus using the p-value to test for a significance of a result, and finally calculating the required sample size. Just to summarize the 4 types of numbers, start with the nominal. When we're using numbers like names, you can tell that 3 is different from 2 and 2 is different from 1, but you cannot tell whether they are more or less. They are just not equal. If you are using ordinal numbers, you can tell that 3 is more than 2 and 2 is more than 1, but they are not necessarily equally spaced. In the interval type of number, they are equally spaced, but there is no absolute zero, and you have negative values and positive values. In the ratio scale, they have all the above properties. They are different, they are more and less, they are equally spaced, and they have an absolute zero. So you can do all possible types of calculations. It can be useful to change a continuous set of data into a categorical or a discrete type of data by using certain thresholds or cut-off points. So you can use this to change a continuous variable into a discrete variable. We do this, for example, with exam marks. We can set up a threshold or a certain cut-off point at, say, 50% or 60%. Anything below this is a fail. Anything above this is a pass. And that way, we can present and summarize the data in a more simpler way, but we also cannot do some statistical analysis because we have lost some of the properties of the data by this type of transformation. The other thing is you've got to be very careful about where to place cut-off points. Sometimes it is natural, like in this curve, for example, that plots recovery after a certain operation with the number of patients. It's natural to have the cut-off points here where you don't have any patients at all. So you can term this group early, this group intermediate, and this group as late recovery. But if data can be used in other ways, sometimes if you are in favor of this particular intervention or operation, you can have your cut-off point here, and then you have only very few late recoveries and mark all the rest as early. Or you can do it the other way around. If you are not in favor of this type of intervention, you can have your cut-off point only here. So then you can have only few early recoveries, and most of the others would be counted as late recoveries. In this presentation, we'll go through not only how, but also why should we be checking the normality of the data sample. Why? Because if we can show that the data has a normal distribution, some very important assumptions can be made safely. If the set of data is distributed normally, we can assume where the central tendency is and how the data is spread around the mean about the central point. And in that case, we can characterize the set of the data with few parameters, and then parametric tests, the more powerful parametric statistical tests, can be employed in the data analysis. We can also make some safe assumptions, like how the data is distributed. 68% would be within one standard deviation from the central point. So the 68, 95, 99.7% we'll go through in a second. We can also have fair assumptions about the z-score and the confidence interval. So it's important to know whether the set of data is normally distributed or not at the very beginning of the data handling. But how can this be achieved? Visual examination of the frequency charts or the histograms can sometimes tell whether the set of data is normally distributed or not with the classic configuration, the bell-shaped configuration, the symmetry between the two sides around the center of the bell-shaped, and the other characteristics of the normally distributed data. But you can also use some specific tests to tell whether the data is distributed normally or not, and we'll go through the QQ plot, the Shapiro-Wilk test, and the Kolmogorov-Smirnov test. The first of the normality tests is a variant of the QQ plot. A QQ plot stands for quantile by quantile plot. A quantile is a point which represents either a fraction or a percentage of the data set. So the 90% quantile, for example, would represent where is the point where 90% of the data falls below and 10% of the data falls above that point. A 30% quantile would have 30% of the data below and 70% of the data above. And the quantile plot basically compares two sets of data, one plotted in the x-axis and the other on the y-axis. And if the two sets of data are very similar to each other, they would form a straight line, and if they are not, there would be some deviation from the straight line. Now, the normal probability plot is a variant of the QQ plot in which we use the set of the experimental data on the y-axis, and on the x-axis we use a theoretical set of data. If the set of values that we have are really very well normally distributed, they should have these theoretical values. So on the x-axis we'd have the theoretical values if all the values are actually forming a normal distribution, and the y-axis would have the actual values obtained from our experiment. And if the two sets of data are quite similar, that is to say, if the experimental set has a normal distribution, then they should form a straight line. But if they're not, if there is some deviation of the way the points are plotted from the straight line, then we know that there is some deviation from the normality distribution. So for example, if the data is not distributed normally, like in here where there is some skewness of the data to the right, and there is some very high scores of the data that are quite far from the central point of the data distribution, rather than having a straight line, these very high scores in terms of their distance from the center, the standard deviation here is 8, standard deviation from the center, or 6, would cause this, because if we plot the actual figures on the y-axis against the theoretical figures on the x-axis, these very high scores and the end of the skewed data would form this deviation from the straight line, and we could tell from this QQ plot that the data is skewed. Conversely, if there is skewness to the left, and we have some very low values here that are quite apart from the central point, there are again either -8 standard deviations or -6 standard deviations from the central part. These very low figures would cause this deviation from the straight line at the beginning of the QQ plot, and again we would know that from this plot that there is this set of data is skewed, and it is probably skewed to the left as opposed to this, which is skewed to the right. Another form of deviation from the normal distribution is the kurtosis. When we have fat tails, we have a spreading of the data well away from the central part, or the aggregation of all or most of the data quite close to the central part. In this case, there will be fat tails, and on the other case, you would have very thin tails because most of the data is quite close to the central part. And again, a QQ plot would show this clearly because of the spread of the data quite apart from the central point. You would have deviation from the straight line at the beginning because of this set of data away from the central part, and you would also have deviation from the straight line at the end, and this would be shown here because again of the very high standard deviation, z-scores, standard deviations differences from the middle point. On the other hand, if there's an issue with thin tails, most of the data is actually in the central part with very little spreading on the two sides, then we'd have another form of deviation from the central line. There will be some deviation at the beginning here because we don't have enough data in this area, and there will be also some deviation at the end here in the other direction because again we don't have enough number of values at this area. In the Shapiro-Wilk test, the null hypothesis is that the set of data is actually normally distributed. So if the p-value is less than the alpha value, is less than 0.05, then the null hypothesis would be rejected, and we know that the set of data is not normally distributed. In this set of skewed data, the Shapiro-Wilk W was 0.87, less than 1, and the p-value is less than 1 in 1,000. So this is an evidence that this set of value is not normally distributed because the p-value is very significant, then this is not normally distributed. The Kolmogorov-Smirnov test is the third test of normality, in which a cumulative distribution function of the set of data, if it is perfectly normally distributed, would form this red line. This is a cumulative distribution function. Any point here would be the addition of all the points before it, and it would reach 100% at the very end. This ideal red curve would be compared to the actual cumulative distribution of the set of data, the experimental data that we have obtained in blue here, and the distance between the theoretically perfect normal distribution and the actual cumulative distribution would form the basis for the Kolmogorov-Smirnov test. And again here, if the test is significant, if the value is less than 0.05, then the normality is rejected, and we know that the set of data is not normally distributed. But if the set of data is not normally distributed and the distribution cannot be characterized by few parameters because the data is either skewed or kertotic or does not have any particular pattern, then you cannot characterize this set of data with few parameters and you cannot use the parametric tests. And then you'll have the alternative set of statistics, the less powerful non-parametric tests. So what can we do if we end up with a set of data that has a distribution like this, which is far from normal? One way out of this is to increase the number of the samples. Every time we increase the number of the sample, the distribution of the data, when it is doubled here, would look more like a normal distribution, and every time the number of the samples increase, the shape of the distribution would come closer to the normal distribution. This is the basis of the very famous central limit theory in statistics, which tells you that the shape of the sampling distribution becomes normal as the sample size increases. This is basically because the standard deviation of the sampling distribution, that's to say the standard error, gets smaller as the sample size increases. The standard deviation would be divided by the square root of the n, or the number of the samples, to obtain the standard error, and when we have a higher n here, you get a smaller standard error of the mean. One last thing, if a set of data is not normally distributed, like this set of data, and you can no longer use the parametric test to describe the data or compare it to other groups, you can do one of two things. You can either use the non-parametric test based on the ranks rather than the actual value of the data, or you can try and normalize this distribution. By normalizing this distribution, we refer to the use of certain mathematical transformation. like using the logarithms of the values or its square root or its reciprocal. And this would bring the distribution of the data to a more normal shape. These are the same set of data, but with its logarithm rather than the actual score. And if you are able to obtain a normal distribution by these mathematical calculations, you can then use the transformed pattern to do all the tests required before transforming it back to its actual score. By this we call a normalization of a skewed distribution or a kurtotic distribution. So starting with a set of data like this, there will be several variables to be analyzed, and each of these variables has a set of data. And if this set of data and the several tests and the several variables are distributed normally, then we can tell where is the middle part of the set of the data, and we can be pretty confident that about 68.2% of the data would be one standard deviation above and one standard deviation below that central part, and that 95% of the data would be within two standard deviations above and below the central part, so that any value above the two standard deviation limit would indeed be very uncommon and would be significantly different from the rest of the data. The same applies if any value of this set is more than three standard deviations or above or below the central part. We would know that this is very uncommon indeed. The chance of it happening is very low, since 99.7% of the data should lie between these. We can also assume, because the data is normal distributed, that any particular value of this has a certain z-score related to how far is it from the central part in terms of how many standard deviations or fractions of the standard deviation, and then we could assign a z-score to any of these values. And this forms the basis for quantifying the z-score. The z-score is a way of quantifying the difference between a certain tumor size, for example, and the average tumor size. So the z-score equals the observation minus the mean divided by the standard deviation. If you have a tumor that measures 43 millimeters and the mean tumor size is 33 millimeters, the difference is 10 millimeters divided by the standard deviation, which is again 10, then the z-score is 1. If the tumor size is 58 millimeters minus 33, the mean tumor size, this is 25 millimeters divided by 10, then the z-score is 2.5. Remember that any z-score more than 2 means that the size of the tumor would fall into the area of less than 5% of the population, so that's rare. And if the z-score is more than 3, then it is less than 1 in 1,000 or so. It's extremely rare. Now, significant or not significant? Let's take this example. In a study of pleomorphic adenomas in the females and males, it was found that we had 4 tumors in females out of 112 and 3 tumors out in the males out of 70. The odds ratio for a female having the tumor is 4 out of 108 is somewhere around 3.7, whereas in the males it's higher at 3 over 67 is about 4.5 or so. So it seems that males are more prone to have more risk, or the odds are higher that they will get a tumor pleomorphic than the females. But is that significant or not significant? We run a test statistic, the chi-square 2x2 test. This would give us a value here, and to see whether this value is significant or not, we check the probability distribution of the chi-square test with a single degree of freedom of 1, which is the case with all 2x2 tests. In this probability distribution, there is a certain point here at the 5% level. Anything more than this would be significant because the results here are quite different from the remaining distribution, so it becomes significant if it exceeds this level here. The value we obtained does not actually exceed this single point, so it is not significant. We know from the odds ratio that there is a difference between males and females. Males are 1.2 times more prone to have the tumor, but the relationship is not as significant because we had only one cutoff point here, which tells us that this value is not significant. So that is one obvious limitation for using p-values in statistics all the time. It's a single cutoff point. The other thing is, why make it always a dichotomy? Significant or not significant, effective or not effective? Well, sometimes the question is a continuum, so you don't have to put on an artificial cut-off point into this continuum to say that anything above or anything below are different. Back to the example here, we know that the odds ratio for males having the tumor is higher than the females. We also know from the confidence intervals that we'll discuss a bit later that the chances can be as high as 5.57 for males having a tumor more than the females. The upper limit of the confidence interval is as high as this. So the effect size here and the confidence intervals give us a better view of the results of the study than just saying significant or not significant based on a p-value. So that's one limitation for presenting results in the form of a p-value. If the p-value is non-significant, we really don't know whether there is actually no differences in the rate of recurrence between males and females, or that we had too few number of patients to demonstrate a real difference. That is to say, a false negative rather than a true negative result. In order to tell whether we have enough power to decide whether there is a difference or not, we need to do power analysis for the study and determine the numbers of patients required in order to show up a difference, if there is actually one. When we conduct multiple analysis on the same dependent variable, that is the output, for example, the time to recurrence for the tumor here, the chance that we commit a type 1 error increases every time we do one more test or put on one more factor into it. So if we have 20 different questions about the effect of 20 different things on the recurrence, and all of them are significant, there is a good chance that one of these significant findings is happened by pure chance, because each of them has a chance of happening by pure chance of 1 in 20. In fact, the p-value, or the alpha, that is here 0.05, should apply to the total number of combination of questions on that particular outcome variable. Say in this example, the time to recurrence. All the questions about the relation of different factors to the time of recurrence should add up to this 0.05 combined, so that you could have some of the tests, for example, at a p-level of 0.04 and others at a level of 0.01, so long as the total number of the tests run on the outcome variable adds up to the p-level of less than 0.05, then you can accept that if these are significant, this is a valid result. One of the techniques for the correction of the p-value in multiple testing is the Bonferroni technique. Here, if you are repeating the test 10 times on the same output variable, and you have set up the p-value at less than 0.05, then you divide this p-value, the alpha value, by the number of tests you have conducted, the 10 in this example, and the resultant corrected or adjusted p-value should be 0.05, and any results of the 10 tests that is less or equal to this would be then significant. They would add up, if you add up the p-value of the 10 tests to the original alpha at 0.05. A second way for correcting the p-value in multiple testing is to use the Holm-Sidak technique. which uses a different approach. Say you are repeating the test on the same output variable, the time of recurrence or the safety margin, 4 times. Then you obtain 4 different p-values for 4 of the tests you have done for the answers for the 4 questions. Now you rank these 4 different p-tests in an ascending way, starting from the smallest p-value you have obtained. In this example, it's 0.005 to the largest, which is 0.04. Now, in the Bonferroni technique, you would divide all of these p-values individually by 4. That's the number of tests you have done. So you obtain a different p-value for each of these 4 tests. But in the Holmes-Sitak technique, you use a different approach. You leave the smallest p-value you have obtained as it is, because it's very small anyway. But the second smallest will be divided by 2. So that rather than being 1%, it would be 0.5%. And the third would be divided by 3. And the fourth largest would be divided by 4. And the fifth by 5, and so on until whatever number of tests you have run on the same output variable. In this way, you would adjust the p-value differently than, not equally like the Bonferroni. You would adjust it in a different way depending on the rank of the p-value in the ascending order. It's claimed that the Holmes-Sitak technique is actually a bit better than the Bonferroni because the chance of getting a type 2 error is less. It would have the same chance of avoiding a type 1 error, but it would have a better chance of avoiding a type 2 error. So it's probably used more. The third way is the Tukey test. It has an interesting name of Tukey's honest significant difference test. Here you apply a different formula, you take a different approach. There are certain constants that you take from tables, depending on the degrees of freedom and the number of tests, and there's a certain equation that the software would calculate, again, depending on the differences in the mean squares and the number of individuals in each group, and it will come up with a certain number, and you look into it, the software would look into the differences between the two groups, all the groups, together, and if the differences exceeds that certain number that you obtained from the calculations, then it is significant. If it's not, then it's not significant. So that's a third different approach to the same problem of p-value in multiple testing. Confidence intervals are based on the standard error of the population mean, and both the confidence intervals and the standard error relates to the population, the whole population, not just one sample. This is just one sample. This is a series of 182 patients with pleomorphic adenomas removed in one single center. The size of the tumors, the diameters are plotted here. The average size, the mean was 33 millimeters, and the standard deviation of this sample was 10 millimeters. But in other centers in the world, there may be another group of patients with larger tumors or with smaller tumors, depending on their setup. How can we generalize the information from this single sample to the whole population? We do this by estimating the standard error of the population mean. That is, we take the standard deviation of the sample and divide it by the square root of the number. The standard deviation here was 10 millimeters and the number was 182, and the square root, we obtain the square root of this number and divide the 10 millimeters with it, and the obtained standard error would be 0.7 millimeters something. So we know now that the real size of the pleomorphic adenomas elsewhere would fall into somewhere between 2 standard errors above and 2 standard errors below what we calculated as the mean of this sample. So we used information from one sample to gain insight by generalizing this to the whole population. So what does that actually mean? We have results of a single study in a single center about pleomorphic adenoma tumor size. And that study, out of several worldwide, had showed that the tumor size mean was 33 millimeters and the standard error was 0.76 millimeters. So 2 standard errors above and below the mean would give us the confidence intervals of the population mean. That is 33 millimeters plus or minus 1.5 millimeters. The confidence intervals are somewhere between 31.5 millimeters and 34.5 millimeters. Within these limits, within this 3 millimeters range, we would expect the population mean to be. And if this single series is repeated 20 times, then 19 times you will find that the mean of each of these samples would be within these limits, and only in 1 in every 20 different experiments or series the estimated mean would lie outside these confidence intervals. That's why the confidence intervals here are called 95% confidence intervals. So the confidence intervals are limits within which you would expect the true mean of the population to lie with a certain degree of certainty. The 3 millimeters between the 31.5 millimeters and 34.5 millimeters would contain the true mean of pleomorphic adenomas worldwide with a 95% degree of certainty. Now, if you want to be more certain, you could choose 99% certainty, but that would entail multiplying the standard error with 3 rather than 2. And that would also widen the confidence interval. So you would have a higher degree of certainty, but with a wider confidence intervals. The width of the confidence intervals are related to the accuracy of your estimation. And if you want to narrow the confidence intervals as much as possible, you would need to increase the size of the sample. Remember that the standard errors are calculated by dividing the standard deviation by the square root of the number of the sample. So the higher the number of the sample, the smaller the standard error and the confidence intervals will be. And now to type 1 and type 2 statistical errors. Type 1 is when you get a false positive, as you can see in here. And type 2 when you miss a diagnosis, a false negative, as you can see in there. The degree of overlap between the two distribution curves and the position of this line of probability, the p-value, determines the type 1 and the type 2 errors, among other things. We usually place this line at the less than 5% p less than 0.05 level in here. So anything more than that would be significantly different than the standard treatment, but that would be a positive result. Most of them would be true positive, but some of them would be false positive. On the other hand, anything less than this level would be not significantly different from the standard treatment, so there would be a negative result. Some of them would be true negative, and some of them would be false negative. The blue triangle here is the false positive, that's the type 1 error, alpha, and the pink triangle is the type 2 error, the beta. We start with the type 1 error. Take this example. If we are running a test for a tumor marker that will tell whether a patient does not have a tumor, those patients who does not have the tumor are from this violet distribution, or those who have the tumor in the green distribution. We have set the probability level at the usual position of equal or less to 0.05, less than 5%. Any data, any results higher than this line to this side of the line would be considered positive, i.e. they have a tumor, and anything on the other side of the line would be considered negative, that they don't have a tumor. Now, if you get a positive result, you can either have one of two decisions. The patient actually have a tumor, or it's a false positive. False positive belonging to this small triangle here, because the data, anything outside this limit would be positive, either true positive or false positive. So data from this small triangle would actually be a false positive, a false alarm. It would indicate that the patient has a tumor, whereas in fact he does not. He belongs to the violet distribution. There isn't much that we can do to decrease the type 1 error, the false positive, except moving this line a little bit further. If we only accept, say, a probability level of less than 1%, then it would the line would shift to this side, because you now accept only a p less than 0.01. But in doing this, you would increase the area of the type 2 error. So although you can reduce the type 1 error by shifting the line by asking for a smaller probability for a false positive, you would actually increase the possibility of having type 2 errors. Now, what does it mean that a certain test in a certain experiment has a 90% power or an 80% power in statistics? This imaginary example may help in understanding what is a study power. Say someone had claimed that he developed a new surgical technique, a new laryngoplasty technique that produced better results than the standard laryngoplasty technique. He said that his results with the new technique is about 90% compared to the usual 80%. In order to prove his point, he set up a randomized controlled trial, study number 1, in which he treated 10 patients with the standard technique and 10 other patients with the new technique, and indeed his results were 90% and with the new technique compared to 80% with the standard technique. That's in reality just one more patient who had better results with the new technique. I'm not so sure that the new technique is actually much different than the standard technique in terms of results. And we ran a 2x2 chi-square test, and the results were insignificant. So there isn't much difference between the two groups that can be demonstrated by this study, as the p-value was 0.531. But he insisted that his study can actually provide a better results than the standard technique, so he set up study number 2, another randomized controlled trial with 100 patients in each arm, and again the results were just the same, 90% for the new technique compared with 80% for the standard technique. This time the chi-square test showed a significant result with the 2x2 chi-square test, although the Yates correction showed that the results were not really significant. So these results are sort of a very borderline type of results. If he continued to do that with another study, number 3, another randomized controlled trial, this time with 1,000 patients in each arm, the same success rate, 90% versus 80%, this time it is very highly significant with p401. So after all, the new technique worked, but to show that it actually worked, you would have to increase the number of the sample study from just 10 to something more than 100, because 100 was just a borderline. And if you go to this extreme high number with 1,000, you are pretty sure that the new technique is actually working. Now to the other side of the story, the type 2 error. Whereas we know that the red triangle is the type 1 error because it is lie on this side of the probability level that we have set at 0.05. The yellow triangle represents the type 2 error, which lies within the limits that we have set, but it actually belongs to the green distribution, the patients who do have a tumor. So although they do have a tumor, the results would be not significantly different from those who don't, and this would be a misdetection rather than a false alarm. By definition, a power of the study is the ability to avoid this type 2 error. So it's the remaining part of the curve. If this area of the curve, the yellow part of the curve, is beta, then the power of the study is 1. This is the whole distribution of the green distribution minus beta. The remaining part of the curve is termed the power of the study. And the more power you have, the less type 2 error you would get. Now, naturally, we would want to have a high power to the study so that it can detect a small difference between the two groups and show a statistical significance. But a word of caution here, clinical significance is not the same like statistical significance. If you have a study with a very high power, like if it's a multicentric study from different centers recruiting thousands of patients, then you can have very high power to your study. So high, in fact, that it can detect very small effect sizes here, like a very small effect size, small difference between the two groups. So it can show that there is a significant difference between two treatments statistically, when in fact the clinical difference is, say, a half day less in hospitalization, or 5 milliliter less in bleeding, something that is not really clinically significant. Remember, statistical significance is not the same like clinical significance, and that's something that would happen if you have very high power that can detect very small effect sizes. Now, to the effect size and the confidence intervals as a better way of presenting results versus the p-value, which would tell you significant or not significant. If we are looking into the difference between two groups, say before treatment and after treatment or after surgery, we don't just want to see whether the treatment is effective or not, significantly better or not. We also want to quantify this. What is the magnitude of the improvement, the size of the effect? Is it better like 50%, 30%, 40%? Quantifying this, not just as a point, but also with a range of probabilities around it, the confidence intervals, is what the effect size and the confidence intervals can present versus the p-value. How would it calculate the difference? The difference between these two groups in terms of how many standard deviations difference between them, a pooled standard deviation between the two. You could tell that the difference from this to that in number of standard deviations equal that certain magnitude, and this is how we quantify the effect size and the confidence intervals. So to obtain the effect size, we use this formula: the difference between the mean of this group and the mean of the other group divided by a certain standard deviation equation from the pooled standard deviation of the two groups. And if the difference between the two means is 0, like the two groups have almost identical means, then the effect size is 0. There is no difference. But if it is more than a standard deviation, this is very high. This will be 1 plus. If it is a fraction of the standard deviation, like a very small fraction, 0.1, this is a very trivial effect. Between 0.1 and 0.3, it's still small. Up to 0.5, it's moderate, but more than half a standard deviation, it's a large difference between the two groups. The other way of interpreting a certain effect size is to go through this table. If the effect size is very high, like 1.4, we know that 92% of the control group would be less than the mean of the experimental group. 92% of patients who had not had the treatment would be worse than the average patient who have the new treatment or the new surgery. If it is 0.8, about 80% would be less than the average patient who had the treatment. If it is 50%, this means that there is actually 0 effect size, because by definition 50% of any distribution would be less than the mean. So if you get 50% of these patients less than the mean of the new of the other group or the new treatment, then the effect size is just 0. In meta-analysis, when we pool results from different centers, different hospitals, for example, reporting the results of a certain operation or a certain treatment, we use the effect size in each of these reports or articles to be pooled together in a single meta-analysis. To obtain a single result, effect size from each of these articles, we look into how the results were reported. If they are reported like discrete events, like dead or alive, cured or not cured, improved or not improved, we either use the odds ratio, the relative risk, or the risk difference. But if the results are continuous, like a certain measurement, then we take the mean difference between the two groups, or we can standardize this by dividing the mean difference by a certain standard deviation that can be calculated between the two groups. We go through this when we discuss the meta-analysis. But when we are dealing with a study of correlation, how two different variables are correlated together, what is the percentage of variability of a certain factor by the variability of the other, we use the coefficient of correlation squared. So if we have the coefficient of correlation like R, 0.6, then its square is about 0.4, which means that 40% of the first variable is related to the other, can be explained in terms of the other variable. 40%, for example, of the increase in a certain variable can be explained by the increase of the other. And now we go to the how to calculate the required sample size for a certain experiment or a study. There are different scenarios. I've enumerated the 8 of the commonest of them here, each with a certain equation modification. They are all based on the same principles, all these equations, but with slight modifications among the different scenarios. I'll give you an example of a single group measurement and of a controlled study continuous data measurement. These are the two commonest types of studies. To take an example, say we are setting up a study to measure the distance between the posterior ethmoidal artery and the optic nerve in adults. We want to know exactly what is the distance, the average distance, and we will set the margin of error that would allow for, and that should be as narrow as possible. Say we choose 1 millimeter because it is surgically important to have a very precise estimation about the distance between these two structures. So you would allow only for a very narrow margin of error, and you want to be very confident about the results, so you choose a 95% confidence, so that if this study is repeated 19 out of 20 times, you would have within your margin of error, you would have the correct estimation here. All of these 19 different studies, only one study would have the margin of errors around the average outside the correct answer. So we start with the equation, and there are three variables here that would need to be identified. The first is the level of confidence, and we have chosen 95% level of confidence. The z-score for this is 1.96, so we'll put here 1.96. The standard deviation of the measurement between the posterior ethmoidal artery and the optic nerve from previous studies or from pilot study should be about 3 millimeters, so that would be plugged into here. And the margin of error that we have chosen, because we want to be very precise, would be 1 millimeter, and that would fall into here. And the equation would then be this amount would be squared, and the required sample size would be this 34.57. This is the minimum. So the actual number of cases, either patients or surgical skulls or surgical specimens, required would be 35 cases. This is one formula used for estimating the required sample size for a controlled study, continuous outcome, continuous data. The number required in each arm of the study for each group will depend on three entities. The first relates to how much you can tolerate a type 1 error, alpha. The second, how much you can tolerate a type 2 error, beta. And the third reflects the effect size, how much difference you would expect between the two groups in terms of their standard deviations. The first entity, by far the commonest level of significance chosen for medical research, is p equal or less than 0.05, and this translates to a z-score for a two-sided study of 1.96. So you'll see this 1.96 being used repeatedly in several equations. The second z-score is related to the power, and the usual in medical research that we use either 80% power or 90% power. If we use the higher power, of course, then we need more subjects in each group. But if we can do with 80%, then we'll have a smaller n. The z-score for the 80% is 0.84 and the z-score for the 90% is 1.28. So these two figures, you will see them repeatedly used. The 1.96 and either 0.84 for 80% power or 1.282 for 90% power. The third entity is the effect size, and this is basically how much difference you expect between the two groups divided by their pooled standard deviation. The higher the effect size, the less number will be required for each sample in each group, and vice versa. We'll go through how to estimate the effect size in the next two slides. Remember that we are trying to estimate the expected effect size before we start the study. So we don't really know how much of an effect size it would be, but we try to have a good guess about how much it is so that we can calculate the required sample size. There are several ways of estimating the expected effect size. One of them, of course, is to look into the literature for similar studies and see how much effect size is there. Or you can have a personal assessment of this, either by a good guess or by a pilot study, or you could try to think in terms of percentage how much you would think there will be a difference between the two groups, 10% or 20 or whatever. The third is to use the special conventions like Cohen's d for the effect size. Cohen had classified the effect size into 0.2 for a small effect size, 0.3 for a medium, and more than 0.5 for a large effect size. So if you have your thoughts about how much you would expect of a difference between the two groups, if it is small, then the effect size you can choose is 0.2, medium 0.3, and if it is you expect a large difference between the two, then you can choose 0.5 or more than 0.5. And if you don't want to use any of these three ways, then you can try and estimate the effect size with special formulas. The effect size can be estimated with the usual formula, but remember that we have not yet started the study, so you plug in figures here that you would expect them to happen. You've not seen the results yet. You would have a good guess about what you expect the mean of the first group would be, what you would expect the second group mean to be, and then you try and calculate the pooled standard deviation of the two groups using another formula. And once you have decided on the expected effect size, you can plug it into the equation plus the z-score for the level of significance and the z-score for the power. And this is just an example about what you can expect the effect size to be before starting the study. Say you have two groups here measuring a hormone or an enzyme or a certain continuous output. You expect the mean of the first group to be about 100 and the second group to be about 90, and you will use these two figures in the equation for the expected effect size. The tricky bit, of course, is the expected standard deviation, because that would require the number you would put into each group and the expected standard deviation for each group independently. And you can fill into this equation if you have sort of a rough idea about what you expect the standard deviation of the first group to be and the second group, and how much you think you would need in terms of sample size. And the equation first for the pooled standard deviation would start with the number and the first group, that's 100, minus 1, that's 99, multiplied by the square of the expected standard deviation, which is 20. So that's the first thing, plus the same thing for the other group. 100 minus 1 equals 99, divided by squared expected standard deviation, the square of 15 is 225. Divided by 100 here, 100 there, minus 2 equals 198. And from this, you would get a figure divided by 198. This is 312, and you take the square root of this, and it is 17.7. So you take the 17.7, which is the expected pooled standard deviation, put it into this equation, minus the mean. The expected mean for group 1 is 100, and the expected mean for group 2 is 90. So the difference is 10 divided by 17.7, and this will give you 0.56. So that would be the expected effect size. Use this into the formula, and now for the z-score for the level of significance, we use 1.96, and the z-score for the power we use, because we are choosing a 90% power, 1.28, and divide this by the effect size that we have just calculated, which is 0.56, and multiply all by 2. Then you get 2 multiplied by 33.5. That is to say, you need 67 cases in each group. This is the other way of estimating the effect size from an estimated pooled standard deviation if you don't want to use figures from pilot studies or from the literature. So for example, if we are setting up a controlled study for continuous data, trying to see if the systolic blood pressure of patients with epistaxis would differ between adult group and pediatric group, that's group 1 and group 2, and this will be a two-sided test, and we have selected the alpha level at 0.05, that's the usual, and have chosen a power of 90%, that's again quite common, and we think that there would be about 10 millimeter mercury difference between the two. This is what we are going to use for the estimation of the sample size. We use the same formula. The z-score for the 1 minus alpha over 2 equal 1.96. The z-score for the power of 90% equals 1.282. The difference between the two groups is about 10 millimeters mercury. We think that this would be the difference between the two groups. We've not measured it yet, and we also expect the standard deviation to be similar to what we found in the literature or what we have found in our pilot studies, to be about 20 millimeters mercury. So we expect the effect size to be about 0.5. So the sample size would be equal to 2 multiplied by the z-score for the level of the significance, 1.96, plus the z-score for the power, 1.82, all divided by the expected effect size, 0.5, all squared. The required sample size would be 83.98. That is the least number of cases. So we need 84 patients in each arm of the study. By this, we come to the end of this presentation on 12 core concepts in statistics. Assalamu alaikum.